And so we're now here at the part where we're going to hear from our colleagues from Ostara, which has been making great progress in nutrient recovery, phosphorus recovery from wastewater, and perhaps other domains. And so we're going to hear from Robert van Springelen, who is involved in brand development and sales and developing this whole business in various dimensions. And so he's going to talk about the business perspectives that Ostara is bringing. And we'll also hear from Matt Kuzma, who's been a partner with the Alliance for quite some time and has been doing a lot of work for quite a while in leading nutrient recovery efforts, especially at Ostara. So I'm going to turn it over to Matt and Robert, who can share screen and take over the slide deck. And so take it away, Matt and Robert.
Sure. All right. So great. Thanks. Thanks for the intro there, Jim. And as mentioned, I'll be kind of cooperating with my colleague Rob van Springelen on this. And not coincidentally, Rob and I kind of represent the two facets of Ostara's business. We have both essentially a water treatment business as well as a nutrients business, meaning nutrients as in recovered phosphate product that we manage, and that's been true, with Ostara since the beginning. So I'm the water person. Don't ask me any fertilizer questions, and I can't speak for Rob, but I suspect he wouldn't want too many water treatment questions. But we're going to change focus a little bit here in terms of scale, moving away from the more I guess less concentrated in terms of nutrient mass loads, and look at how we can produce and improve phosphate fertilizer product and do nutrient recovery on concentrated fertilizer production facilities and their associated waste streams. So I don't think it's new to this organization in terms of kind of the challenges we face moving forward in terms of substitutes for phosphorus. Certainly the world we're living in today and the challenges towards science, we have to navigate our way through that. But as we look at the phosphorus cycle today, we are managing a linear path. Let me just see, there we go, get rid of some of my stuff up top. A linear path, and of course we want to change that away from circular. So as we look at it now, we're mining phosphate rock for the vast majority of phosphorus that's in circulation. We're running it through an industrial fertilizer production facility, transporting that to field, using the crops grown, and then discharging ultimately, which is causing a lot of the point source challenges that we mentioned earlier in Chris Hornback's presentation. So the challenge we want to look at here is that this linear path is about 80% inefficient, meaning one out of, or I guess I should say 20% of the phosphate that we mine out of the ground is ending up on our plate, and a lot of that is ending up off in the environment. So we very much want to look at making this a circular path. So when we look at renewable phosphorus sources, these could be municipal, industrial, or animal waste. We've talked a fair bit about the animal waste in the last panel. Certainly Chris mentioned many of the municipal applications, and Ostara has say 25 operating facilities on the municipal side, but this is going to focus a little bit more on the industrial side. When I'm talking industrial in terms of segment, I'm going to look at phosphate fertilizer production facilities and the associated waste stream. But what we want to look at here is, on the left side, our technology branded as Pearl, how that is structured, and then work our way through the chain here to how the fertilizer is applied. And I'll let Rob talk a little bit about that. So the core technology from our end is the same in all applications in terms of the phosphorus recovery reactor, branded as Pearl. We do make Struvite exclusively, and we make a very high purity product regardless of application, so greater than 99% pure. And Rob will talk more about how that applies. But in a phosphate production site, we have a bit of a broader process design, because these operations don't have a lot of the same infrastructure that applies in a municipal application. We do have to cover some pre-treatment and post-treatment to the Pearl in order to meet their discharge quality standards, as well as to pre-treat the stream to get a suitable stream to us. And so when you look at phosphate mining and fertilizer production applications, there's essentially two different scenarios. One being a closure scenario where the site is no longer in operation. And when the site's no longer in operation, they have a few challenges, because at closure, they stop generating heat. And that heat, as they produce processed water running through the facility, the water coming out of the production facility goes into a pond, and hot water evaporates pretty quickly. Now, the challenge is when you close that facility, you're no longer generating heat, so you don't get the same evaporation. But the ponds exist, and the ponds are continuing to be fed by leaching water from large stacks of phosphogypsum, which is kind of how they manage their water balance. So when we look at a closure scenario, we're going to pre-treat in the first stage to remove fluoride and silica, which essentially create some operational challenges. The silica becomes a gel, which is very difficult to manage in the fluidized bed reactor from our end. So we do some pre-treatment. We use a very similar process to the status quo in the industry, which is calcium addition. In many of these cases, they use what's called a double liming process, where they add lime to precipitate the phosphorus. They run that across a membrane, and then they take that concentrated gypsum up into a large stack. So we will add some lime at the beginning to precipitate out fluoride and silica, but we won't over apply the lime, so that we maintain the vast majority of the phosphorus for recovery. And on the back end, following the reactor that recovers crystal green as a fertilizer, we have a post-treatment on the membrane side. And that post-treatment allows them to generate discharge quality water, and also allows us to recover some of the chemical compounds that are then recycled back to the front of the treatment process to improve the efficiency. But in many of these cases at closure, they have to start treating discharge quality water so that they can reduce the water balance. So if you look at Florida operations, for example, when hurricanes come, they can tend to fill these ponds up to the brim, and there's been long documented history of discharge from those ponds, causing pretty significant environmental degradation and eutrophication challenges. So maintaining water balance and depleting that inventory over time becomes a key objective. In an operational facility, it becomes a little bit of a different scenario, because they're still getting a fair bit of evaporation. But what we can also do is recycle that water within the facility. But very similarly, we can still produce discharge quality water. And that recycled water can then be used for washing and other applications where it's been reduced in phosphorus content. So the reduction in phosphorus content allows them to use it in wash water, so that there's some absorption back into the water in the liquid stream, and then that can be used as process feed water into the production of their core fertilizer, which would be, say, a mono or diammonium phosphate product. And this, so from a process schematic, it's very similar from our end in both situations. The question is really, what kind of volumes of water do they treat, And do they want to recycle that water, or do they want to produce a discharge water? But in both of these cases, we're very much aimed at upcycling that feed stream that has relatively very high feed water concentrations. So if you look at these feed streams coming in, they're phosphorus concentrations in the range of 2 to 10,000 milligrams per liter, pH in the range of 2 quite often. So they're very highly acidic and very concentrated nutrient streams that they're managing. And they recycle that within their operating facility, but they have to manage water balance. So that's where the gypsum application comes into play. So, as I mentioned on the process water influent, pH less than 2. This is from a full-scale application we ran a few years back. Phosphorus concentration of 12,000. Sorry. It does have some ammonia, but not enough to force the full Struvit reaction. But if you look at the discharge on the post-treatment side, we're able to get the neutral pH and single-digit numbers on phosphorus discharges, and this is a bit unique, as well as ammonia, and this is a bit unique in terms of giving them the ability to discharge high quality water from the facility and maintain their water balance, or they can use it back in the production facility and reduce their intake of, for lack of a better word, virgin water. So this has been demonstrated at full scale. This is one of our Pearl reactors operating on a phosphogypsum application. But the other side of it, of course, is that we want to be generating a high quality fertilizer product. And again, Rob's going to talk about that in a minute. But it really puts them in control of their operation, because they're not at the mercy of weather patterns that are impacting their pond water inventory. There's true triple bottom line benefits here in terms of the social impacts as well for these operations. And it's very cost effective against the traditional double liming application, which in some ways is a similar process, but it doesn't recover a product that can be reused in the fertilizer application. Just some visuals here at the bottom in terms of what these operations look like. You'll see the reactor, which is really the core of our process, but many of these other tanks that make up the pre and post treatment for the operation. This is actually a reclaimed gypsum stack that you can see on the side here. But as that water drains down the gypsum stack into this pond here, then we're able to recover the nutrient value from those ponds. And with that, I'll turn it over to Rob to talk a little bit more about how the fertilizer that comes out of these operations is applied and the benefits on that side. Rob, are you taking control, or am I driving for you?
If you could take control. Yes, we're now going to talk about the fertilizers. Something I've been doing for the last 20 years, and always been in specialty fertilizers. I've been working for Scott's Miracle-Gro before. And what we always did was we were selling slow release fertilizers and controlled release fertilizers. So fertilizers that were always slower in the release. And we've seen a lot of benefits about that. Yeah. So taking that in account, we see actually the what's happening in the EU. If you talk about the environmental part of it, the EU on the moment is taking some advantage, some steps, and I think if we look at it in the future, some other continents might be able to follow. Yeah, and a few things on that is that the fact that it's the EU is actually taking the Green Deal. Yeah, so with the Green Deal, what they would like to do is actually lower the exposure of the fertilizers in the waste stream to the environment, actually to promote biodiversity. Now, one of the things they are actually saying is saying, look, we would like to have a mandated recovery up to 50%. One step back, yes, thank you. and mandatory regulations adding recovered phosphate. So what they do in Europe, they're talking about, or if they actually decided to put the new fertilizer law regulation into place, which is in 2022. What's happening over there is that they also put Struvit as a recovered salt. So Struvit, in that case, could be used in the making of fertilizers throughout Europe as a raw material or as an end product. So that's a good step forward, because that means that all the Struvit from municipal waste streams, by the way, will have an end of waste status, and we are able to sell it. So it becomes a lot easier. What's also happening is there's a ban on microplastics. If you talk about microplastics, a lot of slow-release fertilizer are actually slow-release due to the fact that there's a plastic coating around it. Now, in the new law, within 8 years, they have to be proven to be actually recyclable. If not, then they're not allowed on the market anymore. And the good thing about the Green Deal is also that the government said, okay, we would like to cut down on greenhouse gas emissions. Talking to one of the people this week, one of the managers at one of the big potato companies, they said, look, it's simple. If we want to cut down on greenhouse gas emissions, for example, for our fries, about 25% of the total greenhouse gas emissions are actually coming from fertilizers, the way it's been made, that type of thing. And with Struvit, you're actually cutting down your greenhouse gas emissions for ammonium phosphate with about 90%. So it only costs 10% of greenhouse gas emissions versus a normal DAP per kilogram of phosphate. Next one, Matt. So talking about that, we also see the consumer trends are changing. So we see the young people actually talking about or wanting to go more environmental. Research of Nielsen has showed indeed that 60% of the global consumers are willing to pay more for sustainable food. And that's also what you see happening here. So it becomes more aware. But what you also see is that the big boxes or the supermarkets, for example, in Europe, they are actually saying, look, we are willing to pay a little bit more for a product that has been sustainably made. So farmers are forced to use products either organic or less organic, but actually determined or been told by the supermarkets how they have to grow their crop. So we also see some movement over there. Next one. So, but also the farmers themselves. If you talk to the farmers, they said, look, we also would like to look at our the soil health. Soil health is sort of the new trend becoming more and more in the foreground, where they say, look, it's not about giving a fertilizer, but it's how can we feed the soils, and how can we feed the soil and the soil health, the soil biome, and still growing a good crop. Now, Struvit could be part of it, because with Struvit, it's shown that it actually doesn't affect the soil biome as much versus the application of a normal DAP. Next one. And Ostara has been doing this for the last 9 years. We've been doing a lot of trials, and we keep on doing trials while selling also commercially to farmers, and because we want to know more what's happening, because we're actually selling a fertilizer that's not water soluble. Farmers and products that are not water soluble, they normally don't like it, because they've been taught over all these years that phosphate needs to be water soluble, otherwise roots can't take it up. And here we've got a product that is actually not water soluble. So we need to teach them how it works and how it agronomically performs better. Now, what we're showing is actually that we're going to get a higher nutrient efficiency on it. There's no leaching and that type of thing. So if we talk about the product, and I know that Laura Campbell had a question about Struvit. This is in the hands, you see the Struvit. You see how it looks like. It's actually a mineral fertilizer out of an organic waste stream. So, which also means that it's quite high in its nutrients balance. What you see over here, it's 5% nitrogen, 28% P2O5, and 10% magnesium. Yeah, and the product is actually, it's a phosphate ammonium fertilizer. It's root activated. Yeah, it's the roots itself, they exude organic acids, and these organic acids are actually diluting the granule and thereby taking up the product. Now, it's a crystalline product, and for Europe, it's a low salt product, but it's also very low in cadmium, or it doesn't have any cadmium. Yeah, a lot of products in Europe and everything that comes actually from Morocco, yeah, they've got high cadmium contents. So what's happening in Europe is that the laws, new fertilizer laws, saying, okay, you need to get the cadmium levels lower. Now, the crystal green is actually doesn't have any cadmium inside it, so it's actually a perfect product actually to use there. And the good thing in Europe also is that in 2022, yeah, the product can be used in organic farming. So it automatically from the European Union, yeah, will get an organic status, which is good for the farmers, because with the farmers, the organic farmers are currently using bone meal, yeah, or rock phosphate. And it's proven that the Struvit actually has a better uptake, nutrient efficiency use versus the other two. Next one. So what you see here, we put the plants in control. On the photo, you actually see the root hairs actually going towards the granule. So the product itself is water insoluble, as I said before, and it's that root exudates, that it's also the little droplets you see that actually are dissolving the granule itself. Yeah, and here you see a lot of a few pictures. Yeah, if you see, we start on the turf seeds growing. What we did over there is actually we put a substrate of 100% crystal green, Struvit. Yeah, and we put grass seeds on top of it. By putting these grass seeds on top of it, you see in the middle one that the roots grow through it. Now, for a fertilizer, that's unique, because there are no other fertilizers that roots will grow in between, because the fertilizers are too salt. The roots don't want it, they're burning. Yeah? And then in the third one, one step back, the third one, you see actually the root hairs branching out over the granule itself. Yeah? And that's also where the root hairs, the small root hairs are dissolving, because that's where all these organic acids come from. So it's actually embracing it and getting the nutrients out of the granule. Yeah. And the other thing is that it has also an agronomical benefit. So it's not only the fact that it's that's from recovered phosphate. Now we also seen in our what we call signature crops where we know we're going to get a better yield. We see a far better yield, up to minimal ROIs of 3, yeah, so sometimes up to 10. It also depends on the phosphorus content of the soil itself. Yeah, but in general, see from these crops, we really see an advantage by actually using Struvit as a replacement for DAP. Next, yeah. And on top of that, yeah, if you look at the environment, what we did on the top, the top graph, yeah, is we had a control, which is we did some leaching. Yeah, so we put water in it and we measured in the bottom how much phosphorus was still there. The control is just the soil. And then the crystal green is with crystal green. We did the blend with crystal green and a traditional P source. And we did a traditional P source. And as you can see is that the crystal green itself with leaching, it's actually not leaching out. So if there's no root in the middle, there's no root around there, it just stays over there. Now that's the beauty. And also, if you look at the bottom one, we did a surface phosphate runoff. Yeah, we did it at the kind of governmental project in the UK, and we did actually 30-minute rainfall event, and then we actually looked at the water-soluble phosphorus that's been leached off or run off. And we actually saw that if you look at the bottom, there's no runoff of water-soluble phosphorus. So even though there's a heavy rain, if you get somewhere in nature where it shouldn't be, it's still not going to release when there is no root around. So if it runs into water or a water body, it will stay over there, because as long as the water body is there, there's no root, nothing is going to happen. Next one. Any questions?
Thank you, Robert. Thank you, Matt. So we will open the floor for some questions. So you raise your hand in the chat box there, and we'll have a chance to have a conversation or answer some of your queries. I'll just throw one out for Matt while we're waiting. So how long, when did this whole phosphogypsum phosphate mine shutdown operation start? How did that all get going? What's the future for that part of your operations?
Well, we did a full-scale demonstration project a few years back. Some of the challenge with those applications is that their need is very weather dependent. And so if you enter a couple of drought seasons, they seem to feel that the status quo is perfectly acceptable. And then when there's a hurricane season, then they come at you and they want something built, very quickly. But what I would say is that, now that we've demonstrated this at schools at full scale, and we've cultivated demand on the fertilizer side that can absorb these kind of volumes, because these are much larger volumes of fertilizer production that you deal with in the municipal or smaller side application. Each one of these sites could be upwards of 50, 100,000 tons a year minimum. So from that standpoint, we've had to ramp up our fertilizer business significantly. We're just now at the stage where we're commercializing that in terms of a full-scale business model. So that's kind of where we are today, and why the timing for this is relatively synergistic.
Great, thanks, Matt Schultz. We have some questions.
Jim, I think we're actually out of time.
Let's take one. We can
take one. Let's go Paolo Pavanato. Hope I'm pronouncing that correctly. I'm going to ask you to unmute.
Yes, I hope everyone is listening to me.
Yes, we can hear you.
Well, I have done some work with collaboration with people from Germany, also in Brazil, evaluating this Struvite, this kind of crystal green pearls. And we have seen that the results for plants are fantastic. So it's working very well. My question is necessary any minimum level of P in the sewage sludge treatment to precipitate adequately and in a volume for production, commercial production? And also, if you consider the size of the seed, how many people do you imagine in which size of seeds we could establish this plant?
So the first question is really about economics. There's no quote minimum concentration. For example, we do have one project we're working on where there's a significant food processing discharger locally that is coming into a facility, and when you blend the two streams together, their feed concentration there is only in the range of, say, 25 to 30 milligrams per liter. And we've been able to demonstrate economically that we can remove even relatively low proportions, 50, 60% of that, and get them down to essentially traditional municipal influent conditions cost effectively. Generally speaking, the economics are a bit unusual there. So, generally speaking, you're going to look at something in the range of, say, 75 milligrams per liter where the economics make sense. And a very similar comment on the capacity side, because the real challenge becomes the economics of the competitive alternative. And from a scale standpoint, what I would say on the scale standpoint is the bigger limiting factor is the application on a municipal sanitary application is the use of anaerobic digestion, because that's what actually converts the phosphorus back into a soluble phase and generates lots of the ammonia that can become both a driver for the struvite, but also a benefit in terms of the opportunity to recover that ammonia in a fertilizer form. And what you generally see, depending on geographies, is that the scale of facilities that operate anaerobic digesters, kind of falls into somewhere in the range of, say, 50,000 people, population equivalent. Now that varies significantly by geography, but generally that's more the limiting factor, is the presence of the digester as opposed to the number of people.